In this video, we're going to calculate the frequency and energy of a ray of light based off of just its wavelength. So for the system that we're going to be looking at, the wavelength is 440 nanometers. So the first thing that we should probably do in this case is convert the wavelength from nanometers into meters, as meters is actually the standard unit for length. And so what we get is that 440 nanometers is equal to 4.4 times 10 to the negative 7 meters. Another constant that we're going to have to use is the speed of light, which is referred to as c. And so the speed of light is approximately 3 times 10 to the 8th meters per second. And so to calculate frequency, we can use the equation c over lambda, where lambda is the wavelength. And so if we use that equation and plug in the values that we will have 3 times 10 to the 8th meters per second over 4.40 times 10 to the negative 7 meters. And so if we cancel out the meters, what we will then get as our answer is 6.82 times 10 to the 14 per second. And so per second also has the unit of hertz. And so using hertz or per second is both acceptable. And so now that we've calculated the frequency, what we can do is we can calculate the energy of our wavelength as well. And so that equation is h nu. And so h is Planck's constant, nu is the frequency. And so if we replace nu with c over lambda, what we get to calculate the energy is hc over lambda. And so Planck's constant, which is h, has a value of 6.626 times 10 to the negative 34 joules seconds. So if we plug all of these values in that we already have, what we get is 6.626 times 10 to the negative 34 joules seconds times 3 times 10 to the 8th meters per second over 4.40 times 10 to the negative 7 meters. We can see that meters cancel out as well as the seconds, and so what we end up with as our final answer is 4.52 times 10 to the negative 19 joules. And so in this video, what we did is using a given wavelength, we were able to calculate both the frequency and the energy of that light.